Hey everyone, in this video we would like to talk about how to get a complete grid connected PV system using MATLAB program. Okay, so I got this question a lot, and a lot of my own students would like to know how can they get or how can they do a complete PV system inside MATLAB. So I will give you a very small and easy step in order to get it for 100% for free and without any effort. So if we go to a MATLAB website or MathWorks, you will find here a detailed model of 100 kilowatt grid connected PV array. You will see that a system here, a complete grid connected PV system connected to a 25 kilovolt grid using a DC to DC converter and a three-phase, three-level volt source converter. And also you will find everything about this model in details inside MATLAB. Now, how can I get this? First, you will click on View MATLAB command. I will leave this link inside the description. Okay, and then copy this MATLAB command. Okay, now the first step, just to concentrate with me. First you will go to MATLAB, okay, and don't click on MATLAB. Okay, don't click on run command now. First you will click on or right click and then run as administrator. Okay, run as administrator. Okay, not running normally. Now what are we going to do? Now we have the MATLAB here command. We will copy it. Okay, and then go to the command window inside MATLAB, Control V. Okay, and wait for MATLAB starting Simulink. Okay, wait for MATLAB and we will get back. Now we'll find that MATLAB automatically opens this window for the 100 kilowatt grid connect system. This system is similar, of course, to the system provided by the website. So now you can have now a free 100 kilowatt grid connected PV array without doing it inside MATLAB. Okay, so that's the first thing. Second thing, you will find that now we are operating in the accelerator mode in order to accelerate the calculation, okay, for a 2.5 seconds. Now let's see an overview about this model, and then we will run an analysis, and I will show you an error which occurs when you run this grid connected system. So the first thing you will find here is the PV array. When you double click on the PV array here, you will find how many parallel strings, okay, and how many series modules or how many modules in each string. Okay, so the first thing you can select how many parallel strings and how many modules in series. Second thing you will find here is the module data. The data for the module, you will find if you click here, you will find a lot of modules, PV modules for nearly every company. You can see hundreds of modules. Okay, if you select any of them, for example, I selected this one. Okay, you will find it will give you the maximum power. Okay, maximum power generated from this module at, of course, the 1000 watt per meter square and 25 Celsius degree. And the open circuit voltage, short circuit voltage, how many cells, and everything about the data. And you will find here also the voltage at the maximum power point and the current at the maximum power point. Of course, we know that the voltage and the current here representing the value of voltage and the current at the maximum power of 305. Okay, and of course you will find the series resistance, shunt resistance, and so on. Now we will find here also the temperatures. This range of temperatures 0, 25, 50 is the different values I would like to see. If I would like to display IV and PV characteristics of this panel at this given temperatures 0, 25 and 50. Okay, for example, array at 1000 watt per meter square and specified temperature, this one which is 0, 25 and 50. If I click on plot, okay, you will find here the current and voltage, the relation between current and voltage, and the power and voltage at the different temperatures. You will see this curve for 50 Celsius degree, this curve for 25, this curve for 0, and as you see that when the temperature increases, the maximum power decreases. Okay, this is the 0 Celsius degree and this is a 50 Celsius degree. Okay, and also the relation between current and voltage at a different temperatures. Okay, so you can here simply plot the values at a different temperatures using MATLAB very easily. Okay, and you can select what you would like to see. Do you would like to plot the array, or I would like to plot the array at a specified irradiance. If I click on this one, for example, I would like to plot at 1000 and plot at 250, okay, at this temperatures for the array at a 25 Celsius degree. Now if I click on plot, it will give you two curves, one at 250 watt and another one at 1000 watt. You will see the difference between the two curves here in power versus voltage, and the current versus the voltage. Okay, now if I would like this one, I will click on apply and okay, but I don't want to change anything. Okay, now another thing here is that you can see here, this is a scope for the irradiance, the change in the irradiance, and a scope for a change in temperature. If I go to the irradiance, IR, and temperature, which is input to IR and input to temperature, irradiance and temperature, and this port is for the measurement. It provides you the different measurements of the PV panel, and this is the positive and the negative for the PV array, the last 2 points for, or the equivalent of this system or the PV system. Okay, now if we double click on this one, the irradiance and temperature, okay, you will see that here this is of course the default model. This model have it changes, which is already done. You can change it as you would like, but this is for just an illustration. Okay, so you can see that here, for example, from 0 to nearly 0.7, I think 0.7 here. Okay, the irradiance 1000. Then it will provide a slope, okay, decaying, okay, at 1.3, okay, or 1.1, whatever, at this point, which is 250 watt per meter square for the irradiance. Then it changes again, increases again up to 1000 watt per meter square. And also for the temperature, 25 Celsius degrees, then it changes suddenly to 50 Celsius degree. Of course, you can change what you would like to do, okay, by clicking and dragging, but I don't want to change anything. Okay, so this is, you can here change whatever you would like to do. This one you can choose it like this, move it like this, up and down. Okay, but I would like to keep it at 1000. Okay, and you can change the temperature as you would like. This representing the change in the temperature in real life, a change in the irradiance in real life, and we will see what will happen when this changes go to the panel, okay, using MATLAB. So close this window. You will find this part. This part is the post converter, okay, and this is the controller. We have a D block converter. This one prevents the operation for the operation of the post converter and the inverter, except after a certain time. If we double click on this one, you will find it, the step time is 0.05. Before 0.05, the inverter and the DC shopper does not work. Okay, starting from 0.05, it starts to operate. That is the function of this block. Now this one is used to generate pulses for the converter in order to produce the maximum power. Okay, so this is considered as maximum power point tracking controller, as you see here, maximum power point track controller, using a method called the incremental conductance. Okay, you will see that it takes a measurement board for the voltage and current of the PV panel, voltage and current produced from the panel, input to this controller, and by adjusting its own duty cycle in order to produce maximum power from the PV array, it will produce an equivalent pulses to control this post converter. Okay, if we double click on it, you will find that it has a frequency of switching 5 kHz, and the initial value of the duty cycle of the post converter is 0.5. Okay, so this is the post converter. Now we have here a DC link input to the 3-level bridge, or the 3-level voltage source converter, or the inverter here. Okay, and also have its own controller. This is a controller for the VSC, or the voltage source converter, or the inverter. Okay, you will see it takes the VABC primary, IABC primary, or the 3-phase voltage and 3-phase current. These values are the 3-phase current, and for the voltage is the 3-phase voltage. Okay, VA, VB, VC. Okay, you will find here VABC underscore B1 and IABC underscore B1. What is this values? This values after the transformer connected to the utility grid. Okay, or it is the current and the voltage connected to the utility grid or injected to the utility grid. So this is simply a measurement port. Okay, a 3-phase VI measurement. Okay, you will see that it measures for the voltage phase to ground. Okay, and it's simple as VABC B1. That's why it's called VABC1 here. This one representing the values measured here. And for the current, IABC B1, okay, this one is the phase currents. Okay, so this block is used for measurement, and we named it as B1. This one is a step-up transformer, takes the output voltage, which is 260 volt, from the 3-level bridge, and converts it to the utility voltage of 25 kilovolt. Okay, we have also here a capacitor with inductance. What does this do? This is used as a filter. Okay, the output of a 3-level bridge voltage is not a pure sine wave, so we use this 10 kilovar filter in order to remove harmonics and make it a pure sine wave. Okay, the inductance here, of course, or the line here is used as for smoothing the current. Okay, so the current going out from this bridge is of course a pure sine wave. Okay, so what does this level bridge? It's consisting of this controller, which provides pulses to this one in order to do two functions. The first one, inside it consisting of 2 loops. Okay, we can discuss how does this controller work in another video using research papers, but for now we will provide an overview. This controller consisting of 2 loops, or 2 inner controllers. One, or the external loop, is used for regulating this DC link at 500 volt. Okay, the internal loop controls this DC link at 500 volt, and the internal loop, which is a current controller, used to control the output current to produce a pure sinusoidal current. Okay, and you'll find here this one, all of this are, and this one, double click here, all of this are measurement ports. Okay, now So the output of the 3 level go to a filter, then a step up transformer connected to the utility grid. If we double click on the utility grid, you will find here this is ABC, which is the output from here, this 3 terminals going to the utility grid through 5 kilometer feeder, 14 kilometer feeder, and we have here a 2 megawatt load, another 30 megawatt and 2 megawatt load, and then we have another generator which is considered as the largest generator or the utility grid, for example, and a step up transformer from 25 kilovolt to 120 kilovolt, and supplies power to this load with, of course, a grounding transformer, zigzag grounding transformer. Okay, so all of this are ready inside the MATLAB itself. You can change what you would like and see the results. Okay, so that's the first thing. Second thing, if you run the program, okay, it will take some time. Now the MATLAB completed the analysis. Okay, now but before we continue, I would like to mention a common error happening. Okay, you will find that sometimes when you run this command and starting this play button or starting the analysis, what will happen is that it will give you an error and that you would need to change the operating folder. Okay, so in order to do this, you will click here on browse for folder. Okay, then for example select the desktop. Okay, for example desktop, and then click on select folder, and this error will be gone. Okay, now let's get back. Now after running the analysis, let's see the output. Okay, first let's see what let's see first the VA and IA, the voltage and current going to the grid. Okay, here. Okay, now let's make this one like this. Okay, and then use this one at this point. Okay, so this is VA, the voltage of phase number A, and the current of the phase number A. Okay, this is a pure sine wave and this is a pure sine wave. Okay, this is what is going to the grid. Okay, okay, now let's see VA VSC, the output voltage from here before the harmonic filter or before having the capacitor bank with a filter. Okay, so let's click on what? This one, VAB VSC SC, double click on it. Okay, this is the output of the converter or the inverter. Okay, let's zoom in like this. Let's zoom in again. Let's zoom in again. You will find something here. Here at the beginning, a pure sine wave. Okay, this is before the converter and everything works. Okay, it is an open circuit. Okay, and then it starts working or generating waves here at 0.05. Remember that here it is 0.04. At 0.05 here it will start operating. Remember that this one, not this one, the D block converter, double click on it. It has a step time of 0.05. So at 0.05, this one will operate the boost converter and the 3 level. Before it, it will not operate. Okay. So before this, you will find that the 3 level bridge or the output of the 3 level bridge is connected directly to the utility grid. So the voltage of the utility grid will be similar to the voltage measured by here, by this scope or go to tag VAB. Okay, so at here at 0.05 before it, you will find that it's the measured voltage is similar to the grid voltage waveform. Okay, starting from here, the 3-level converter operates. Here 1 level, 2nd level, and 3rd level. Okay, so let's restore view. Let's take this sample time. Okay, let's zoom in like this. Let's zoom in again like this. Okay, so you'll see that here 3 levels. Okay, because it is a 3-level converter. Okay, of course this is not a pure sine wave, close to sine wave but not a pure. Now after using the harmonic filter, okay, or the capacitor bank here, we will have the output like this one. Okay, restore view like this. Okay, this is the voltage out, a pure sine wave. Okay, another thing, let's see another thing. The duty cycle. Okay, we need to see this one, VDC. Okay, double click here. And let's make it like this. Okay, this is the value of the DC link. You will see that the DC link at 500 volt. Okay, the DC link is regulated by using the controller inside the inverter itself. Okay, it has a DC regulation especially for the DC link. Okay, another thing is that I would like to see the duty cycle. Okay, so let's go to here, this one. Okay, this one, it has a duty cycle and V average. Double click here. Okay, you will see that here at 1000 watt, then goes down to 250, then go up. Okay, this is the power average. This is the power generated from the PV panel. You will see that here it goes at 100 watt, then at 245 watt or 25 watt, I think. Okay, we can zoom in and see. But anyway, you will see that here at 1000 watt and 25 Celsius degree, the power generated is close to the maximum power. Now let's see the V average. This is the output from the PV panel. Okay, if we look at here, at the beginning it was more than 300. More than 300, this value was the open circuit voltage. Okay, then at a certain time, as I remember, 0.005 of the D block converter, here at this instant, 0.05, you will see that it starts to change and go down, fluctuates. Then the V average goes to a steady state, a certain steady state value. Okay, here. Then at this instant, the duty cycle changes from a value to another. Okay, so let's restore view. Okay, so at the beginning, it is a V average at the duty cycle of 0.5. It is at a certain value. Then when the duty cycle changes, the V average changes, and so on. You will see that the duty cycle changes using the controller here. This controller, it changes the pulses, which changes the duty cycle of the converter. What will happen is that it will lead to a change in the V average. Okay, changing the duty cycle will lead to change the V of the PV panels. Okay, we discussed, of course, how this one operates inside our video of the maximum power point tracking controller. Okay, so I think that you understand now how can you get a 100 kilowatt or any value of a grid connected PV array, and how can you do the analysis. And we see now all of the components of the PV system, and how can we see the changes in every component. Okay, now in another video we are going to discuss how does the maximum power point tracking techniques work. What I mean by this, if we double click here at this sign, you will find a block inside it, and if we double click we have another block. We can discuss in another videos how each of these blocks, you will find a block in another block like this. How does this blocks operate using research papers? Okay, I'm going to get research papers and I will discuss them in details. Okay.